the definition of extended binary trees is given here. And we saw this last time. We drew a few elements. We decided to represent those objects that were generated by this recursive definition by drawing some dots and lines on a piece of paper. And we said, well, these things that you draw like this, when you take a pen, draw it like this, those objects are a binary tree. So for example, here's one object that is a binary tree, an extended binary tree. Okay. Now, I'd like to copy this definition of an extended binary tree here. And I'd like to define a new kind of recursive structure. This time, we'll call this new structure a full binary tree. The definition will be very similar. However, the kinds of objects that this new definition will generate will differ, not in significant ways, but in some ways, from the definition of an extended binary tree. So here's a definition of a full binary tree. And here on top, you see the definition of an extended binary tree. What's the difference? So this is what we're defining now. Full binary trees here. Again, because it is a recursive definition, we have a way of generating in the basis step some new elements. Okay, so this one, you'll notice that there isn't much difference in the recursive step, but there is a difference in the basis step. The basis step no longer tells me that this empty set, this guy is one of the elements of the set that I'm now defining. And so we're now defining a set of full binary trees. Apparently, the empty set is no longer in that set of full binary trees that we're defining. But a single vertex, this guy, okay, so basis step, generates this dot. And it says the dot is a full binary tree. Okay, so now let's see what else is generated by this definition. How about the recursive step? What does the recursive step generate? What kind of, so here's the definition, you can probably see it. So meanwhile, here's the recursive step. What does this rule tell me? What kind of objects are there? And again, this is only because we're visual beings. We're drawing some dots with lines on a piece of paper. Someone who's perhaps more adept at expressing these ideas in sound, for example, or in music, will represent it completely differently. We draw it because it's the easiest for us. So what is a recursive step? What does that say? It says take one of these guys and attach the trees that you already have in this set. So what kind of trees do we have in this set so far?
2 full trees.
What is a full? Okay, 2 full trees. And what are the 2 full trees that we have so far?
Like, what are the characteristics, or is it just T1 and T2?
Okay, T1, yeah, okay. Maybe
those are just single roots, right?
Yes, yeah, exactly. That's what I was asking.
Okay.
Yeah, so you take a root and you attach the left subtree and the right subtree. The only left and the right subtrees that we have so far, okay, are just roots, right? So we take the only 2 trees that we have and we attach them to this new root, the purple root, and draw these lines. That's what the rule tells me. That's the way of generating new trees. So now this guy is generated. There is no way, notice, for me to generate this kind of structure here that I was able to generate with extended binary trees. There's no way for me to generate this kind of binary tree, extended binary tree. But I can generate this kind of tree. So notice, apparently, so later I'll let you think about this. Is it true that anything that our new definition generates can also be generated from the definition of an extended binary tree? That's question number 1. Question number 2 is the converse, which you can answer right now. Is it true that anything that's generated by the definition of an extended binary tree, the recursive definition, can also be generated by the definition of a full binary tree? And the answer to that is no, because clearly the extended binary tree definition from last time generates an object like this, which cannot be generated by this definition of a full binary tree, by this one. Okay, so fine. So this is the tree generated at the next step. Is there anything with one application of the recursive step that I can generate at this stage? So is there any new trees that I can possibly generate? So I've looked at the basis step, and then I've looked at one application of the recursive step. There's nothing else I can generate. But if I can apply the which I get to another time, apply the recursive step another time, and I get to apply the recursive step an infinite number of times, then what kind of structure can I draw now that I can point to and say this is a full binary tree? So again, going back to maybe
each T1 and T2 will have two more.
Yes.
Two of each.
Exactly. Just to have it here somewhere. Okay. Okay, so here's another one that we can generate, apparently. Take a new root and attach to it T1 and T2. Well, what's T1 and T2? Well, in place of T1 and T2, I can place any one of the trees that I've been able to generate so far before the application of this step. So I have two kinds of trees for now. I have this guy and this guy, the only kinds of trees that I have. So I could take this, and I could take this and say that this is a new tree. Is this a full binary tree? Does it fit the definition? Right?
No.
Why not? Why not? What's wrong with, how does the definition not apply, please? So I'm going to take a new root. Let's try another one. And I'm going to have, let's do this in gray. So I get to attach the left and right subtrees to this. And in place of T1 and T2, I get to draw any of the trees that I've generated so far on the previous steps. Okay, so this recursive step, again, it's a rule for generating new elements. And the rule is here, right here. Okay, so I get to draw a new root like this and attach to it new elements, T1 and T2, that I've generated previously, and that will be my new tree. Okay, so let's attach this to the roots of T1 and T2. That's what the rule says. And in place of T1, I can have, for example, this tree. How about let me take as T1, let me take this tree here. Let me already erase this T1 and T2 here, just like that. So I'm going to attach this guy that I generated in the previous step. Okay, to the right, I'm going to attach just a single dot. Why can I do this? Because I've generated that dot here on the base during the basis step. Is this one of the trees that I get to generate according to this step? Let me try one more. And my claim is going to be that I only get to generate 3 trees at this stage and no more, no less. Okay, as T1, I'm going to take the tree that I generated here on the first, the second. So this tree is going, and then I'm going to take another one just like it and go ahead and attach it to the new root. And I'm going to say that this guy is now, these are new T's. Three new T's were generated at this step. Does that make sense? Or are there any objections to this? Let's try one more recursive step. So we have 2 recursive steps. Let's try one more. Third recursive step. Now you help me. Okay, this will be our working definition of the structure that we're defining mathematically. Okay, the recursive definition is what we'll work with today. Okay, so help me out. Let's generate at least one more. Not one more, a few more, but help me draw the next one. So what do? You guys see this definition, or is it too small?
Yeah, it's a little too small.
Yeah.
Okay. How about this one?
Yeah.
Okay. Okay. So these are our trees. So let's generate one more. So what do I, so let's say in words, what do I get to do on any step, including this one? Can someone say it in words?
There are many different cases that we can.
Yes, but that's true. But what are we doing at this step?
We're gonna have again T1 and T2 if we want to name them.
Okay.
That we have to connect them to the previous, to the one of the previous cases, to one of the nodes in the previous recursive step.
Okay. So it's okay. So it's I know you know this, but so it's not that we're connecting the two trees now to any one of the trees in the previous step, but rather, as the definition says, take a new
To a root.
root.
To a root.
And these are the T1 and T2 are the trees that were generated in the previous step, right? So I get to connect this new R to these trees, right? To the roots of those trees. Now, in place of those T1 and T2, I can have any one of the trees that came before, right? Does that make sense? So let's just pick how many possibilities do we have actually. It's a good exercise to have write down a general expression and the number of trees that are being generated at the 57th step or nth step in general. But here, so far, we've generated how many? Let's count them. 1, 2, 3, 4, 5. So any one of those 5 trees can go in either one of the positions for T1 and T2. Okay, so let's, for instance, can we like pick in place of T1, can we pick this guy? Just,
Yeah, yes.
Okay, so let's do that. So let's draw this guy. And in place of T2, let's just take, just of all the trees I could have taken, let's just take this one. Okay, so it's this, 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 this. Apparently that's a full binary tree. Okay, let's draw one more. Here we take a root and we connect it to 2 full binary trees that we've had before. In this case, let's take, in both cases, let's take this guy again. Okay, so now we're going to have like this guy, looks like this, like this. And we're going to call this guy a full binary tree. Now, you've seen full binary trees before. Maybe you didn't use a recursive definition, but if you've seen full binary trees from before, does anyone by any chance, obviously you don't have to, but remember the definition? There are several alternative definitions. You could Google it and get some definition. I don't know what comes up first. But does anyone remember? Like in memory, obviously you can Google it. But so one of the definitions that you might have learned is that these are, so you, it's not, so what, we need some terminology, and it's okay for us to talk about this terminology now because the next topic of the class will be graphs, and we'll have to define this terminology anyway. So
I remember something about classes between the nodes.
Classes?
Mm-hmm. Yeah, I think that I cannot remember exactly, but something about the number of nodes that are in each class, something like that.
Yeah, like, I think maybe like you have to have 2 children for every parent, something like that, basically.
Yes, that's what I was asking. The second one. Yes. So, so here's the thing. We first need this bit of terminology that everybody has heard, but let me just repeat. So each of these guys, these dots are called nodes or vertices, alternatively, right? In the context of graphs, those branches that you see, those lines, these are called, well, branches. In the context of graphs, these are called edges. This node here is called the parent to these 2 nodes. The root is the parent to these nodes. So you have a dot or a vertex or a node from which 2 edges emanate. The nodes on the other end of those, on the other ends of those edges that emanate from that original node are called the children of this node. Okay, very loose definition. So for example, this guy and this guy are children to this guy. Does that make sense? Okay, sometimes this is called the left child, this is the right child, but just children. Okay, and this guy is called the parent to these 2 guys. Okay, that's just the terminology. Now, and obviously I'm using the term guys for nodes, okay? So how about these two nodes, or these two guys? These two nodes, they have one parent. They're called siblings to one another. The nodes, these guys, that do not have children of their own are called the leaves. Okay, so for example, here in this tree, this guy, this guy, this guy, this guy, this guy, this guy, and this guy, these red guys, those are called the leaves. The other nodes are called internal nodes. Okay, this guy is one of those internal nodes that has another special name called the root. Okay, so what distinguishes full binary trees from other kinds? You may have heard of complete binary trees, for example, which is simply binary extended binary trees with already defined, again, a recursive definition, is that each node either has no children, in which case it is a leaf, like these guys, like these guys, or it has exactly two children, right? You cannot have a situation, if it's a full binary tree, cannot have a situation like this, for example, because this guy here has just one child. Okay, this guy does have two children. This leaf has 0 children. Okay, but when when we're talking about full binary trees, and there's no way for you to have like any node to have just one child. Either has 2 children or has 0 children. Okay, but we're not defining full binary trees that way. That will be a consequence that you can prove now, that very fact will be a characteristic of full binary trees that were defined recursively. All these alternative definitions can be derived from this particular definition. Okay, and that's just showing that these definitions are equivalent. It's just an exercise in logic. What other quantities do you know about trees? Let's say stick with full binary trees. So these are full binary trees. Again, the full binary tree is an object that we recursively defined this way. That's what we mean by a full binary tree now. The fact that any of its nodes can have either 0 or 2 children, we haven't proved it yet. We don't know that. Now, the reason I'm mentioning this is maybe that's the way when you first saw full binary trees, maybe that's the way you defined it and you just forgot it. Okay, it's definition. Now I'm going to apply it somewhere. Maybe write a program to use it in some context or something. These trees have applications in practical problems like search problems, for example, and a variety of other places that these structures are used. You'll see that in the data structures course if you haven't yet, and throughout algorithms courses. But we're concerned with just this definition. What else did you see? What do you know about the tree? So, for example, yes, please.
The idea of balancing them or having a balance.
The balanced trees.
So like that tree that you just highlighted is balanced.
Yes, that is true. It's also called a perfect tree. Okay, that's kind of like a data structures topic. There is a need to sometimes build these trees in a balanced way, particularly in search applications. That is true. Okay, here's what that's a good point. Here's what I'm asking. What is the height of a tree? Okay, so when you talked about balanced trees in particular, you probably have seen this in a data structures course, right? I'm just guessing, or an algorithms course. You had to talk about the height of a tree then, before you even defined what a balanced tree is. What is
it the steps that you need to take from a root to get to a leaf?
That's exactly right. So now we're going to have our own definition, which is not going to be that one, but that's exactly the definition, right? That's what I was asking for. So the height of this tree, so you may, so it depends on the authors, okay? So depending on what textbook you used, you talked about the height of the tree. You may have differentiated from the depth of the tree, yet another quantity defined over a tree. You could have defined it as the number of nodes on the longest path from the root down to the tree. You could have done that, right? So here, the height of this tree, for example, is going to be 1, 2, 3, right? Because the longest path, so here, let me draw another tree just in case here. This is our scratch paper. Let me move this aside. First, please tell me if this is a full binary tree. Is this a full binary tree? This is going to be an unbalanced tree. Oh, let's draw it this way. Is this, according to our definition, is this a full binary tree?
Yes.
Yes, it is a full binary tree, right? Okay. What's the height of this tree?
5?
Yes, right. That according to the definition that you gave before, right? So 1, 2, 3, 4, 5, the number of edges there. You may have also defined depth of the tree as the number of nodes on that path. So that would have been 6. Okay, so this is, by the way, this is the longest path. We need the longest path to the leaf. Okay, but these are all very intuitive definitions and they all make perfect sense, right? So, but we're going to define this in a very different way. Let's write down the height of this one as well. What's the height of this tree? The blue tree? 3, right? So our definition of the height will be recursive. And that recursive definition will be tied, notice, I'll give a definition in a second, how closely it is tied to the structure of the tree. By the structure, I mean the way we build these trees at the recursive step of the definition from the trees that are previously known, as we just did a few minutes ago. Here's the definition of a height of a tree. You take a tree, and we know how we're building the trees. We're taking a root and attaching to that root 2 trees, T1 and T2. T1 and T2 to that tree, to this new root. We're saying, so let that be this 3T built during the recursive step of the definition that we had before. The height of this tree is defined as 1 plus the max of the heights of T1 and T2, right? Here's T1 and T2. This is T1 and T2. That's the definition. That's the definition here. Well, what does that mean? It's a recursive definition. Think in terms of a recursive program. So when I built this tree, I took the root R here and attached to it 2 subtrees. This guy, T1, and this guy, T2. What this definition says, that the height of T is going to be 1 plus whatever the largest is of the heights of T1 and T2, right? Of T1 and T2, okay? So that's what it is. Well, but everybody sees this now, or okay?
Now we have to do the same thing for T2.
Exactly. So let's get that 5. So it's going to be 1 and then plus, and then
Plus
here
1.
Yeah, 1
plus
max the heights of, let's use a different color. Let's go with the blue. So here's T1, let's call it T1 prime, and let's call this T2 prime here. This guy, it's going to be T2 prime. Right? So what does that work out to? Well, I don't know, but that tree itself is a recursive structure. It's built recursively. So it's going to be 1 plus this tree, T1, like 2 primes, and T2. Let's say 2 primes on the second step. And so on. So people get the idea, right? And when you go on, where do you end? Where do we end?
But it will be 1. The height of the last one will be just 1.
Yes, the last one will be 1. Why? Because the basis step. Okay, so according to the basis step, what's the height of this tree? According to the basis step. Now I'll be asking basis step of what? Should be asking a basis step of what? You should say, well, you didn't clarify which basis step do you mean? And let me ask you back that question. Which basis step do I mean? Maybe I'm lost. According to the basis step, what's the height? What's the height? I need some way of stopping this process. Is what I'm talking about. When you wrote your recursive functions in an introductory programming course, you needed the base case where your stack frames would stop, right? What's the height of this tree? So this is a tree that's generated during the basis step of the recursive definition of the tree itself, right? Remember? So the basis step generated just the dot. It's a full binary tree that was generated by the basis step. What's its height? Well, I need some rule to tell me what the height is, right? So I better look for my definition. If I forgot the definition.
Is it 1?
No. It's whatever the definition tells me. And I peek into the definition. And that definition has a basis step that tells me that the height of a full binary tree that has just a root in it, let's define it to be 0. That gives us the guarantee of the stopping. So the height of this guy is 0. What's the height of this tree then?
One plus 0.
1 plus max of 0 or 0. Exactly. Right? Do people see this? The height of this tree is going to be 1. And that's consistent with the intuition that you had from before when somebody first defined the tree and told you that the length of the longest path from the root down to the leaf that's farthest away from the root is going to be the number of edges in that path. Okay, so here that longest path has just one edge on it. And our definition is consistent with it. Now, we haven't proved that this definition gives the same quantity, but at least we haven't seen any contradictions yet. There's consistency. And indeed, you can prove that this consistency carries on. We're not going to bother with it. It's just an exercise in logic. But here, coming back to this example, so the height ends up to be 5 because at some point, in fact, at the next point, I will have to stop. I will end up with this. I'm dropping the parens now. Okay, so I will end up with this, and this will end up to be 5 at the very next step. Does that make sense? Right, that's a recursive definition. So notice what we have, just to recap here for 1 second. And while I'm recapping, let's open the check-in to see how many people are still here and how many people are sleeping now or in the nearest coffee shop or tempted to go to sleep. So please check in now while we recap. And then we'll see if the number of people present drops sharply here. Okay, please check in. Okay, now let's recap. So notice what we have. We have a recursive structure. The tree itself is a recursive structure. On top of that recursive structure, we have defined a quantity, the height of a tree. The definition of that height, of that quantity, is also recursive. It's very closely tied to the recursive way of generating new objects that are full binary trees. Does that make sense, the last 3 or 4 sentences that I just said? Another quantity, let's define another quantity and finally prove some kind of theorem after all this discussion. Okay, so again, this being, so we want to be very sort of precise in our definitions. Now, yes, we have these intuitive notions that come from our previous acquaintance with these objects, trees we've seen before, right? But we're defining them strictly, recursively, and then next we're going to prove something about those quantities. The next definition that we need is also going to be recursive. Notice again how tightly it is connected with the recursive definition of the full binary, with the definition itself of the full binary trees, which is recursive in its structure. What do I mean by this? Well, if I ask you, well, what is n of t is simply the number of nodes in the tree, all of the nodes, leaves, internal nodes, or whatever, every dot. Well, you can see, why do you need to give me a definition? I can look at the trees that you draw and just count the number of dots. And yes, you'd be correct. That's a definition. If I ask you for a definition, you'd say, well, look, why are you even asking me? It's obvious. So just look at the tree and count the number of vertices, and you'd be correct. But first of all, well, there are at least a couple of things wrong with this, if you want a nice definition. One is that, what if it's a tree is large and you can't really count? Let's give a recursive definition of that quantity, the number of nodes in a tree. So here's the nodes in the tree that I want to define. NT, number of nodes in a tree. And again, I'll have a basis step. I'll say that the root, if I just have the root, that is the object, the full binary tree that's generated at the basis step of the recursive definition of the full binary tree. That root, n of that root is going to be 1. So root, see root, that's just one. The number of nodes, there's one node. Okay, now you can say, yes, I can count that. I see the one node. You'd be correct. But we're putting this down on paper, registering this. That's true. And then I have a recursive step of the definition. And this recursive step tells me that if I have constructed at some step, at the 20 millionth step of the recursive definition of the full binary tree, and I have T1 here, and this is done by the 20 millionth, at the 20 millionth step. Recursively generated this tree right now. It can be super high, okay? Okay, so, but its structure is still the same. It's a recursive structure. At that 20 millionth step, I just took one node and attached the left and right subtrees. Now, each one of those subtrees can be super deep, but that's another story. So the number of nodes for this tree here, let's call this T. This T is this guy, the whole new tree. The number of nodes is going to be simply 1 plus whatever nodes I had in T1 and whatever nodes I had in T2. And that's going to be our working definition. This definition, maybe, yes, you'll say it's obvious to me, a visual being. That aside, is it clear what the definitions are? So we have a recursive definition of a full binary tree, and then on top of that tree, we're defining two quantities. And now we want to say something after all of these definitions. And the something that we want to say is this statement. So this is going to be our theorem. We want to prove this. We want to say that there is no way, if you have a full binary tree, for the number of nodes to exceed this quantity. Okay, now you may say, oh my God, what does that even mean? So before we get to proving this, let's first parse the meaning of this, right? So let's figure out what that even means, okay? So let's work with these trees here. Let me redraw this because so let's take this tree. Let's take something small. Let's start with a small one. Let's take this one is a full binary tree. It fits the definition, can be generated. How many nodes do I have here? Well, here let's cheat and let's just simply count. So just simply 1, 2, 3, 4, 5. I have 5 nodes. What's the height of this tree?
2.
The height of this tree is 2. Is it true that n of t, the number of nodes of t, less than or equal than 2 to the height of this tree plus 1 minus 1?
Yes.
Yeah, it's 8 minus 1, that's 7. And that side is 5, so that works out. So here's another example. That was example 1. Example 1. So we're trying to make, what are we doing these examples? We're trying to make sense of what this theorem says. What is it asking me to prove? Let's do another one. 1, 2, 3, 4, 5, 6. Okay, so do I need more? Okay. Okay, let's take this one, fine. Is this a full binary tree?
Yes.
Exactly. What's the number of nodes?
Eleven.
11. What's the height?
3.
The height of this tree is 3. Is it true that 11, which is the number of nodes in the tree, less than or equal than 2 to the height of the tree plus 1 minus 1, which is going to be 2 to the third plus 1 minus 1, which equals 15. It's true, right? It works out for these two special cases. Okay, well, but that doesn't, I'm still not understanding. So why should that be the case? Okay, so let's try, when do you think why is it less than or equal? When do you think that the equality will hold?
When there's only one, when we only have the root.
Okay, let's actually draw that one. When we only have a root, so that was this example. So that's example 2. Let's call this example 2. Example 2. Let's make example 3. If you just simply have one root, what's the number of, so this is our t. What's the number of nodes?
1.
1. What's the height?
0.
0. Is it true that 1 is less than or equal? So 1 is the number of nodes in the tree less than or equal to the height of the tree plus 1 minus 1. Is it true? Is it true? Does it hold? It holds as you predicted, right? And also that we have an equality here in this case. When else can we have an equality? Notice, by the way, this is as a side note, this is pretty typical in math. So before you even start to prove anything, you're trying to make sense of it, right? You're just doing all this scratch work. Most of math is just scratch work. And then the published paper can be like 2 pages. I've seen PhD dissertations that are 2 pages long, just 2 pages. Which is the result of years and years of work, 2 pages. And then, of course, on the other extreme, you have like 1,700-page dissertations. Okay, but leaving that aside, will this hold here? Here's a tree. What's the height? What's the number of nodes here?
15.
The number of nodes is 15. What's the height of the tree?
Oh, sorry. 3.
3, exactly. Is it true that n of t, which is 15, is, let's go gray again as before. N of t, which is 15, less than or equal to the height.
Do we have the equality every time the tree is balanced, fully
Yes,
balanced?
I think it's the
Yes,
same every
so
time.
people have this hunch, right? Yes, but we see the problem is we haven't defined balanced trees. This is a balanced tree, it's true, and you've seen these balanced trees. This is actually a perfect full. It's also a complete binary tree. If you've seen complete binary trees, it's yet another kind of tree that differs from a full binary tree. This is a perfect tree. So yes, notice. So you've noticed that this works exactly. So it's 2 to the 3 plus 1 minus 1, which is exactly 15. It's 2 to the 4th, 16 minus 1, that's 15. So we do have this 15 equals 15 here. 15 is less than or equal 15. And here we have an equality that holds, right? Now, suppose this extends even further. So let me just, okay, so this was our example. So let me put this. Just to account for the nodes, how many nodes are there now in this new tree that I've drawn? That's going to be another perfect binary tree. Full binary, it's going to be a full, let's stick with full. There's another full binary tree. How many nodes do I have? This, did somebody mention levels before also? When you said classes, by the way, what did you have in mind?
I meant levels, by the way, yeah.
Okay, all right, so how many levels, how many nodes do I have at this level?
1, 2
1.
to the 0.
Okay, 1. How many nodes do I have at this level? What's anyway, my point is, what's the total number of nodes in this perfect binary tree? I know.
31.
Yeah, it's 31, right? It's going to be 2 to the 5th minus 1. 2 to the 5th minus 1. Why is it 2? I'm just pointing drawing your attention to some related but a different fact. This 5 is the height plus 1 according to our definition here, this exponent. Why is it that? If I simply count the number of nodes, just simply point and just count them. Just point them out and count them like this, but level by level. If I do, then I have the sum of the powers of 2, which by the way, you've proved this in one of the homework assignments, that 2 to the 0 plus blah, 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 2 to the n minus 1 is going to be 2 to the n minus 1, right? Didn't you guys prove this in one of the homework assignments? The sum of the first powers of 2 is going to be the next power of 2 minus 1. People proved this, right? In one of the homework assignments. So here you have it. You have 3 plus 2 to the 4. That's going to be 2 to the 5th minus 1. And that's, of course, 31. You have 31 nodes. Before, you had 15 nodes when I went only up to the third level here. Then you had 2 to the fourth minus 1, which is 16 minus 1, which is 15 here. Now we have 31. If I draw one more level, so help me out, how many total nodes will I have? It goes up by a power of 2, well, minus correction of a minus 1. If I drew one more level, how many nodes would I have? Help me out. And we're done with the examples. Now we have to prove this theorem.
63.
So exactly. 2 to the 6th minus 1, which is 64 minus 1. The next power of 2 is 64 to the 6th. Minus 1. So 63 nodes. If I did this process again, like attach 2 nodes here, 2 nodes here, 2 nodes here, blah, 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 filled out this level completely, I'll add, here, how many nodes will I be adding at this level? Actually, I'll be adding 32 nodes there at this level, right? Because right now I have 16 nodes at this level. And every time I add another level, I'm attaching 2 children to each parent, to each leaf. Each leaf now becomes a parent with 2 children, exactly, when I'm filling out this tree. So I'm adding twice as many nodes every time as I had the number of leaves. Okay, so here I have 16 leaves, and I'm adding 2 more children for each leaf. That's like total of 32 now I add to this. So I'm adding up all these powers of 2. And I'm getting the next power of 2 minus 1. Okay, so enough of that. That you actually, by the way, this one you proved using induction. So it works for any n. So you proved this using induction before. Okay, so now let's go back. Now let's prove this. So what I'm going to do is I'm going to copy this because we filled out this piece. And now we're going to prove this now using structural induction. First, let me be very clear what we mean by proof by structural induction. If anybody knows, please remind us. Proof, and we'll write this up. Maybe we'll get, we'll add one more scratch paper here. Proof is by induction, structural induction, which is yet another variant of mathematical induction. What do I mean by this? Here on this slide here, it says structural induction. Here's the definition. What we need to do, so we're proving this inequality holds that we suspect to be true. We kind of like, through these cases, a bunch of examples, and we're kind of beginning to get a sense that that equality probably holds. Now we want to prove that it does. So what the structural induction tells me is that I want to verify that the equality, I want to check 2 things. First, I want to verify that the inequality holds for the object that's generated during the basis step of the recursive definition of the full binary tree. Okay, so improving some fact about, like that inequality, for example, about a recursively defined object, in this case, full binary trees. I need to check 2 things. Whatever the recursive step of the definition of full binary tree gave me, does my inequality hold for that object? That's number 1 thing to verify. That's equivalent to the basis step of the mathematical induction. The next thing I want to verify is, given that this inequality that we're trying to prove holds for the subtrees T1 and T2, which are present in the recursive definition of the tree, of the full binary tree itself. So recall how we're defining this full binary tree. We're taking a root and attaching T1 and T2 as subtrees to it. Provided that this inequality holds for the 2 subtrees T1 and 2, does it continue to hold for the new object that I've generated at this recursive step of the definition of the full binary tree? If it does continue to hold, then the inequality will hold for every object generated by this recursive definition. That's the essence of structural induction. That will become clear when we prove it. But does it make sense at a high level, what I just said? So just to, anyone would venture to repeat in their own words, obviously, what I've just said? Okay, so we,
Well,
yeah, yes.
I can try.
Yes, sure, please. It
The
doesn't
base-
matter, by the way. It's right, wrong, just what matters that you try. Yes.
Okay, so the basis step of the structural induction
Mhm.
has we have to check first that the basic step we gave in the definition of the recursive of the binary tree holds the whatever we want to prove, that it holds for that. And then in the recursive step, we have to prove that whatever we want to prove, that it holds for the T1 and T2, which were defined from the recursive step in the definition of the binary trees.
Okay, so almost. So can I make a slight correction in the second one? So we get to assume that that equality that we want to define holds for that T1 and T2.
And then we want to show that the next ones will be correct. Okay.
Yes. So now, how about everyone else? Like, does this make, for those of us who are involved, if it doesn't make sense still completely, that's fine. But do people get a sense of what we're trying to go after, at the very least? And we'll see this. Now we'll do this on an example.
Yes, this makes sense.
Makes sense. Okay, great. So now let's actually try to prove this inequality here. And let me, just in case, copy the definition itself of the full binary trees. So what we're working with is the definition of the full binary tree and these two definitions here of the height. We need those definitions of the height and of the number of nodes in the tree. So let me copy all of this stuff and have those somewhere nearby. So I'm going to copy these two. So we'll need that. And let me place them here, I guess, here. And then we need the definition of the tree itself. Oh, I hope we're not running out of time. I hope that's not going to happen. Okay, well, it's okay. We'll get to graphs later. But and let me copy this definition here real quick. And that goes here. Oh, I can't resize it? Yeah, I can. Okay, anyway, so you get the idea. Okay, so anyway, proof is by structural induction. So basis step. So again, as you've just told us, at the basis step, we check that whatever is generated during the basis step of the definition of the tree, and there's only one root that's generated there, and I want to show that the number of nodes in the root, which is just 1, is less than or equal than 2 to the height of the root plus 1 minus 1, which is, what was the height of the root by definition?
0.
0 plus 1 minus 1. And that is going to be 2 minus 1, and that's 1. So basis step is correct because 1 is less than or equal than 1. So 1 is less than or equal than 1. 1. So the basis step holds. Everyone agrees? The basis step, no problem, again. Now, the next step is the recursive step. Recursive step. The recursive step, what are we proving? That the number of nodes in the tree that we're building. So notice now, so this T that I'm constructing, this T, let's just draw it on the side. So I have a new T like this, T1 and T2. This is my new T. This whole thing is my new T. The number of nodes in that T, I want to prove in the Simpsons cloud. We're getting to, I want to show that at the very end of the day, that this is going to be less than or equal than 2 to the height of this tree plus 1 minus 1, right? This is what I want to show. Assuming that this inequality holds for T1 to T2. So what do I get to assume? Assuming that for T1, the number of nodes in T1 is less than or equal to the height of T1 plus 1 minus 1, and the number of nodes, so I get to assume this. T2 is less than or equal than the number of nodes in T2 plus 1 minus 1. Does that make sense? So that's what it means to prove something using structural induction. So I want to show that the number of nodes in this tree that I've generated at the recursive step of the definition of the full binary tree, the number of nodes there, is going to be at most this quantity. And for me to show that it's going to be indeed at most that many, I get to assume that for the subtrees of the recursive definition of the tree T itself, for T1 and T2, for those subtrees, that inequality holds for those subtrees. Are we now on the same page? So we've just repeated your suggestion, right?
So then the basis step is just analyzing the root, and then the recursive step is this analyzing the subtrees of the root, but we don't need to then go into the subtrees of the subtrees if there are any, correct?
Yes, that's correct, because at this step, just like with induction, right? When we assumed what we wanted to do in mathematical induction, we wanted to show that from PK, PK plus 1 followed, right?
Yeah.
So when we just talked about PK and forgot about all the previous Ks, in case of the simple induction, right? So all the subtrees, just as we're not going to care. We're going to assume that whatever's built up on the previous case, that holds there, right? Does that make sense, right?
Yeah.
So you're correct, right? What
Okay.
you said is correct.
Thank you.
For this NT, the number of nodes, by definition, what is the number of nodes? It's 1 plus the number of nodes in T1 plus the number of nodes in T2, right? According to the recursive definition. Everyone's with this? That's just wrote it down. I just wrote down the definition. Now, this is going to be smaller than, now I'm using these guys. So instead of n number of nodes for T1 is going to be smaller than twice the height of T1 plus 1 plus minus 1. Okay, so minus 1 plus twice the height of T2 plus 1 minus 1. Everyone agree? Does everyone agree? I just substituted that. Now I'm going to need your help here. We'll be done in 2 lines, but we need to justify those 2 lines very, very carefully. So first of all, I'm going to cancel these this one with that one. So I'm going to say that I have 2 to the height of T1 plus 1 plus 2 to the height of T2 plus 1 minus 1. Now this expression is getting close to this one. I have a minus 1 isolated here, but instead of these 2, I want to argue somehow that the height of this tree, I want to get the height of this tree T itself, right? The height of this tree itself. So now I have the heights of the subtrees here.
Can we check the recursive step of the definition?
Of the height? So let's
of the height, yeah.
Of the height, let's check that. Let's write it down. The height of T is going to be 1 plus max of height of T1 and height of T2, right? Is that what you, let's write this down and have it here for reference, right? Good idea to have it here. So continuing this, now, here's what I want to say. Let me do this green here. I have something like 2 to the, I don't know, 27th plus 1. And this guy, I have 2 to the, I don't know, like 18th plus 1. Okay, let's consider these 2. Here's what I want to write down. That this is going to be smaller than 2 times the larger of these 2. Okay, so let me first write down is less than or equal than 2 times max of, let me carry it, of this guy. Do you agree that that's the case? Do you agree that that's the case there? So what I've done is I have 2 terms, right? 2 to some power plus 2 to some power. These guys. One of these is larger. They could be equal, but let's take the general case. Let's say one of these is larger. Let's say this one is the bigger one. Okay. If I take twice the bigger one, I'm getting a bigger quantity here on the right-hand side, right? So I had this plus this, and I'm taking, so I have two terms, A plus B. And I'm taking twice the larger of the two. Let's say if A was larger. Instead of A, I could have written down like max of A and B. But anyway, I'm taking the larger of the two. So this holds, right? Now, do you also see that this guy is what I've written here? What I've written here is max of 27 plus 1 and 22 plus 1. So max of the exponents themselves. Do people see this? So what I want to say here is that this is the same, this piece.
You mean 18, right?
Oh, yeah. 18. 18 plus 1. Yes, exactly. So what I'm saying here is 2 times 2 to the max of h of t1 and h of t2 plus 1. Do people see this? Right? And if you have no objections to this, then we are done in one line. Then what you see here, why did I go through this trouble? Because this guy, first of all, I forgot the -1 here should carry over. But this guy in the exponent is the height of the tree, right? So what I have is 2 times 2 to the height of the tree -1, right? That's that in the exponent, this guy in the exponent, this guy is the definition of the height itself. Do people see this? And what's the final last step here? Let's just do a color. 2 times 2 to the height is 2 to the height plus 1 -1. Is this blue expression exactly what's in my Simpson's cloud or what? And that's what we wanted to prove. Does that make sense? I mean, you have to like reread this, but it's easy to miss something. But if you follow the discussion, it's easy to recreate. Now, the only way to learn this kind of stuff is to see a bunch of proofs like this. And the way you do it in your own mind yourself. So having seen somebody do it, like at this lecture, reading the text, maybe there's some video, I don't know. But at the end of the day, no matter what you do, you have to recreate this in your own mind. Preferably write it down when you're alone in your room, nobody's disturbing you, and then it will be clear. The clarity will come when you're at peace with your mind yourself. Okay. And sometimes it may come when you think you're not thinking about it, and your mind is just thinking about it. But anyway, so we have a few minutes left. The goal was to continue with graphs, and we didn't do graphs, but that's okay. So you have a similar problem. Now, there are many facts that you can prove about the trees. So one of the homework questions is asking you to relate the number of internal nodes with the number of leaves or something like along those lines. There are a bunch of facts that you could prove. So you have as an exercise one such fact to prove. Again, using structural induction along the lines of this proof here. But this was a nice case, the typical case of a proof by structural induction. You have a recursively defined set. You have some quantities that are defined on that set. Well, not necessarily a set, it's structural. In this case, it's a set of full binary trees. Then you have quantities defined on top of these trees, on these trees, like the height of the tree, the number of nodes on the tree. Both of those quantities were recursively defined. And we related those quantities. In this case, we related them in an inequality. Both of these quantities, this guy and that guy, were recursively defined. And we related them. And we proved that that relation was true by relying on the recursive structure of the definition of the tree itself. So that's the bottom line. The summary, the 3-sentence summary of the entire discussion of today. Okay, are there any questions about this? We should end here.